Okay, good. So we've just finished our calibration with our short, open, load, or through. We then attached these to the end of this cable to make sure our calibration was correct by noting that when we have a load, we're in the center for S11. When we have an open, we're on this side of the Smith chart. When we have a short, we're on this side. We can also look at S11. When we have a load attached, S11 should be low. We measured minus 25 dB. And when we put an open or a short on this, it should either be here or here. This is for a short, this is for an open. And finally, when we connect the cable to here, you should see that the S21 goes to 0 dB, meaning there's no loss. All right, now that you've fully calibrated, you can simply take your calibrations out, but you'll need to leave your adapter. So the device we're going to test for this lab is this cable. We're going to measure the electrical length of the cable and its loss and the phase shift through the cable with our VNA. What's important to remember is we've calibrated the device to the end of here. So whatever we connect between this connector and that is what we're measuring. This cable is not part of the measurement because calibration removed all of the effects. So what we'll do is we'll attach this adapter. We can immediately see our Smith chart says there's an open out there, which is correct. I'm going to attach my cable. And you already start to see something very interesting. First off, you can see that there's a circle. Why would there be a circle? Well, we learned in class that if there's a quarter wavelength, we'll take an open and create a short. And what that means is if the end of this is open, a quarter wavelength of transmission line would get us here. But also a half wavelength, if this was a half wavelength, it would bring us back to where we were. It would be an open. If this was three halves or 1.5 lambda, it would bring us back here. 2 lambda would bring us back here. 2.5 lambda, 3 lambda, 3.5 lambda. And as you can see, we would rotate in a circle as the frequency sweeps from 500 to 1.5 megahertz. Now, what we're going to do is I find the Smith chart here is a little bit distracting. So I'm going to go in here, I'm going to go to my traces, I'm going to turn off the Smith chart. There we go. And what I notice is I want to focus on my phase. So what I'm going to do is I'm going to select my phase trace, which is this one here. And I'm going to go to Format. And let's see, I can do phase. Let's see what else we've got here. By the way, there's some very interesting things, polar, real, imaginary, but let's go back to phase. And what I can see is I have a phase shift here. What I'm going to do now, so we can see our phase is changing as we go. And that's because the phase shifts from this open. But we'll take a look. Let's go ahead and connect this to S21. There we go. This makes everything a little clearer. So now we've connected up, and what we can see is we're measuring the phase shift between the end of our first cable through this second cable. The phase shift through here is fixed in time, but since we're sweeping in frequency, you can see that our phase changes relative to the frequency. You can also see that our S11 has these peaks. These are the times we go from an open to a short, an open to a short. Now this is 50 ohms, so S11 is pretty low, but we can see a little bit of the artifacts. What I'm going to do now is I'm going to unhook it. And I'm going to attach a short on the end. No, I'm just going to leave it right back here. And what we'll do is we'll show you in the lab how to calculate the electrical length of the cable based upon these dips in S11, and also from the phase shift that we have here. And we'll show you how to measure the length of the cable and also the speed or relative velocity of the cable. The only thing that we'll not do in the software is you need to go out and get a ruler and measure the length of your cable. And that's the only piece of information you'll need along with your information on the plot here. And with that, we've done everything we did here on the Nano VNA. This will be much easier to read on the computer. Don't forget, calibrate first, then connect it to the computer, and you should be able to see everything on the screen. All right, we've attached our Nano VNA up to our computer, and you'll notice the screen on the Nano VNA is stopped updating because we're using the computer display. So the first thing we've done is change the frequency to 800 megahertz to 1 gigahertz, and we've done that in order to see just one rotation around the Smith chart. Now what we'll do is we'll place a cursor on the open and short ends. So we already have a red here, which is on the open side. And now we're going to place the green on the short side. You'll notice he's using a pop-out window to better see this. There we go. And hit close. And now what you can see, if we zoom in, is that the red marker, if this will focus for us, the red marker is at 960 megahertz and the green marker is 876 megahertz. The difference between that is the frequency that it takes to go all around the Smith chart. And that tells you the frequency difference for a quarter wavelength, because a quarter wavelength will take you from one end of the Smith chart to the other as you go from an open and short. Now look inside your lab and you'll be able to calculate the wavelength. Let's just go look at S21 so we can see the phase shift and then also the dissipation.
So we need new charts.
So we go down to the display and we're going to change to S21 phase and change the Smith chart to S21 log. And now what we can do is we can see that the now we have to connect the cable to port 2 of our VNA to measure S21. There we go. So now we have our measurement cable. This is our device under test, which is the second cable, and now we'll examine S21. Can we pop out that chart? So let's just move the pop-out chart over. Just grab it and move it over. And we can see that the red marker is at approximately 960. It gives you the values for the impedance at that point, and if we scroll over, we should be able to see. There we go. So the value is minus 1.2 dB, which means that our cable has a loss of 1.2 dB. Now let's pop out the phase chart. And we zoom in, and you can see that we have an initial phase that moves down to 180, and then it just wraps right back up here. So these two pieces are continuous. It just gets to 180. And we could measure the amount of phase shift between the red and the blue, and we can see that the S21 phase is 137 at the red, and on the blue, is down here, it's 90. So if we go back to the pop-out, we can see 137 and 90. We know the two frequencies, and we can figure out the slope of that phase line from here. So as you can see, you can access all the same data on your screen as you can inside of your VNA. Now we're going to change our setting to S11Z. And we're going to get rid of the S21 phase. And what you'll see here is that we have a peak. What's happening is our device under test is an open here, but for every quarter wavelength, that open is going to become a short. So here, it is a low impedance. Here, it's a high impedance. So at the low impedance, we have this open being a short, and at the high impedance, we have the open being an open. And so what that means is the frequency difference between those two is the difference of the frequency for this being a quarter wavelength. Let's go back and reset our frequency to 500 to 1.5. Just a reminder, we've set everything to continuous sweep. So we've got to stop it, and then change that to 500 and to 1.5. All right, now let's pop that out again. And now here it's easier to see. You see we have a repetition of short, open, short, open, short, open, short, open, short, open. Now it's not a true open, but you can certainly see where it's short and where it's open. And from the difference in frequency, and given that you know the length of the cable in front of you, you should be able to calculate what the speed through the cable is and what the wavelength is, because the difference in frequency between this point and that point are exactly a quarter wavelength.